Springs. Here are your priming questions. For the period of a spring, the equation that we use is T, the period, is equal to 2 pi square root m over k. You should notice that this equation is very similar to that of the period of a pendulum. So remember, the period of a pendulum, T equals 2 pi square root L over g. The main difference here is what's under the radical within the square root. Here it's m over k. T is going to be in seconds, m is the mass in kilograms, and k is the spring constant in newtons per meter. Okay. For this, remember the relationship between period and frequency. If you have a problem that asks or give you the frequency, then you'll need to convert that into the period using that relationship. Remember that they are inverse relationships. All right, so for energy in an elastic spring, when you have a spring, and hopefully you saw this from the online simulation, as you bring it down, you displace it from its equilibrium position. The equilibrium position is simply where, if we left it alone for a long enough time, where would that mass hang on that spring? When we pull it down or push it up, we are displacing it from that equilibrium position. When we displace it from that equilibrium position, we give that system potential energy given by this equation. So the potential energy of this spring system, PE, is equal to 1/2 K, the spring constant in newtons per meter, A squared, where A stands for the amplitude, which is going to be the maximum displacement measured in meters. And so we have a maximum displacement on two ends, where it extends the spring and where it compresses the spring. At both ends, the potential energy stored in the spring is given by that equation. So PE is equal to 1/2 KA squared. Now, as it passes the equilibrium position, so if this is the equilibrium position, and let's say it was compressed, as it is traveling down, as it passes that equilibrium position, all of that potential energy has now been converted into kinetic energy. And so we can use our kinetic energy equation from all the way from first term, 1/2 mv squared. And in this case, we use an mv naught to show that this is going to be the maximum velocity. Because once you go beyond the equilibrium position, you're going to be either compressing or stretching the spring, and there's going to be a restoring force. Only as you pass the equilibrium point do you not have a restoring force, meaning you'll have the maximum velocity. Now, to come up with some equations, we can do some derivations. Here, what you see, I've set the two equal to each other. And essentially, this is going to be the energy at the equilibrium position, and that's going to be equal to the energy at the amplitudes, the maximum displacement. The total energy, the E total, always remains the same, regardless of where we are in the system. Right now, we're considering this to be an ideal system, no friction, no air resistance, none of that. And so the change in total energy, the delta ET, is going to be equal to 0. And that is what allows us to use this as an equation. And so you can already see the bottom part of this equation. What I'm going to do is I'm going to go ahead and divide by 1/2 on both sides. So I get mv naught squared is equal to K A squared. And then I'm going to solve for my V naught squared. So this becomes V naught squared is equal to K A squared over M. And here you can see a typed out version of that. This is one of our equations. V naught squared is equal to Ka squared over M. And remember, the V naught, the V sub 0 here, that refers to the maximum velocity. So this is going to be the max velocity as it passes through the equilibrium position. Or you can also think about it as zero displacement. There you go. Now, how would you calculate the velocity of a spring between the amplitude and the equilibrium? And so this is where I'm going to derive another equation for you. And we again use total energy. And in this case, it looks a little bit different. We've added another 1/2 kx squared here. And the reason for this, if we go back up here, At the maximum displacement, all of the energy is potential. At the equilibrium position, all of the energy is kinetic. Whereas when it's not at the maximum displacement and when it's not at the equilibrium, when it's between the two, it's going to have some kinetic energy and some potential energy. And that's what is shown by this. This is going to be the kinetic energy. This is the kinetic energy. This is going to be whatever potential energy it has. And this is equal to the energy at the amplitude. So this is going to be the total energy here. And so what I'm going to do is I'm going to rearrange this and work it out so we can get another equation, and actually two equations, so you can see what we can do with these equations. All right, so again, get rid of the halves since they all have them. So we have mvf squared, and the vf is going to be the final velocity, or you can think of it as the velocity at whatever position we're talking about. So mvf squared plus kx squared is equal to ka squared. Now in this case, I want to be solving for my vf or vf squared, however you want to do this. And so I'm going to start moving things around algebraically to do that. And so I'm going to move my kx squared over first. So I have mvf squared is equal to ka squared minus kx squared. I'm going to pull out my k. So I have mvf squared is equal to k times a squared minus x squared. And here the x is simply the displacement from the equilibrium position. So that's where the position that we're looking for the final velocity. And now I want to isolate my vf squared. So this becomes vf squared is equal to k over m times a squared minus x squared. And so here we have an equation that relates the final velocity to the spring constant, to the mass, to the amplitude, and the displacement. So if we have those variables, we can solve for anything that we're missing out of this set. The next thing that I want to show you is if you don't have some of these variables, you can still use this equation in a special way using a substitution. And that's what I'm going to show you down here. So this is the equation that we just derived. The v squared, which is the vf squared, is equal to k over m times a squared minus x squared. The next step here is actually to factor out an a squared from inside the parentheses. Now at first it looks like you can't, but if I pull this out, that puts a 1 here, and if I try to pull one out from over here, that puts an a squared in the denominator with the x squared. If you have questions on this, we can go through this more in class. But the purpose for this is that I have a k over m times an a squared. And hopefully this looks familiar to you because k over m times a squared, or k a squared over m, that is equal to the initial velocity, or the maximum velocity. And so we can replace this whole term with our maximum velocity, or v naught squared. So if you're given the maximum velocity, but you don't necessarily know the k constant or the mass, you can still use a modification of this equation that looks like this one here on the bottom. So v squared equals v naught squared times 1 minus x squared over a squared. So these two equations essentially are the same, but you use them in different scenarios. So let's try a practice problem. A spring stretches 0.15 meters when a 0.3 kilogram mass is hung from it. The spring is then stretched an additional 0.1 meters and released. Calculate the spring constant. For this one, we can start listing out our variables. We have 0.15 meters, 0.3 kilograms, so we can say our mass is 0.15 meters. And in this case, when we add this onto our spring, it stretches by 0.15. Oh, I messed that up. The mass should be 0.3. I was looking at the wrong number. So this should be 0.3. And that should be in kilograms. Mass is 0.3 kilograms. And then I have 0.15 meters. And here, we're looking for the spring constant. So we're looking for the K. And at first, it looks like we don't have enough information. Now, if I were to draw this out, so we have a spring, and we have a mass on the bottom of it. When we attach it to the spring, it's going to apply a force to the spring, and it's going to drop the spring by a certain amount, and it's going to come to an equilibrium position. This is the distance that's given to us, the 0.15 meters. For this, we use Hooke's law. So we have F is equal to kx. You'll notice that I dropped the negative here because the negative just tells us direction, and if we already know the directions with the forces and the displacements, we don't need to worry about that for our calculation. Now what you might be wondering is, we don't have the force, we have the x, but we're looking for the k. So we need to find the force. In this case, if we have a block with mass m, the force in newtons is going to be the weight, the gravitational force. And so in this case, we can do 0.3 times 9.8 is equal to k times 0.15, which gives us a k value of 19.6 newtons per meter. And if we use our significant digits, this should be rounded to 20 newtons per meter. There we go. So that's for part A. If we're looking at the amplitude, that's the maximum displacement. That's actually given to us. When we displace it or stretch it an additional 0.1 meters, that's going to be our amplitude. It's going to be 0.1 meters. Our maximum velocity, this is when we use one of the equations. So we have v naught squared is equal to ka squared over m. Now that we have our k value, we're going to plug in 19.6 because it's going to be a better value for us. We use v naught squared is equal to 19.6 times 0.1 squared over 0.3. When you solve for this, you should get, actually let's just go ahead and go to the answer. You want to check my work just to make sure that you're getting the same numbers. You should get a v naught of 0.8 meters per second. So that's going to be for the maximum velocity, 0.8 meters per second. Next, we're looking for the velocity when the mass is 0.05 meters from the equilibrium position, and this is when we're going to use the other derived equation. So we have vf squared is equal to v naught squared times 1 minus x over a. These are all squared. And so we're looking for vf, so vf squared is equal to 0.8 squared times 1 minus 0.05 squared over 0.1 squared. And when you work this out, that should give you a final velocity of 0.7 meters per second. Again, you want to work these out to make sure that you have the same answers. For the last one, this is a bit more of a thinking problem, maximum acceleration of the mass. And so when we're looking for the acceleration, we have to think back to first term. And this is going to be with forces. So acceleration and forces, so you should be thinking F equals ma. And now, if we think back to what we just learned recently with Hooke's law, we also know that F is equal to kx. And remember, the reason why I've dropped the negative is because we already know the direction, and that's all the negative tells us. And so, these forces are actually going to be the same, and I'll show you that. So if we think back to our spring with the mass, when we stretch it down, it's going to have the maximum force applied to it when it's at that maximum displacement. And so, we can calculate the amount of force that the spring is going to apply to the mass at that displacement. And so we have our force is equal to our k value, which we can use as 19.6, and our amplitude is 0.1. So the maximum force is equal to 1.96 newtons. And we plug that into our Newton's second law. So we have 1.96 is equal to the mass times acceleration. 1.96 is equal to 3 times a. So the maximum acceleration is going to be equal to, I'm sorry, this is 0.3. This will be 6.5 meters per second squared. And if we go back to our sig figs, this is going to be an acceleration of 7 meters per second squared. There you go. This is the last problem that I want to leave you off on. Practice this. Check your answers with the person next to you when we get to class.